This is the screencast for section 10.2, example 7. Now remember back in example 5, I told you that I was going to go into the direction of motion a little bit more detail in a new example. Well, here's that new example. Basically, our direction of motion is described by velocity. I mean, think about that. When we had vertical free fall in pre-calc, if the velocity was positive, the particle was moving up. If the velocity was negative, the particle was moving down. Or here in calculus, if the particle is moving right along the x-axis, the velocity was positive. If it was moving left, the velocity was negative. Well, now this particle is moving multi-directional, infinitely many directions. So we're going to describe its direction with a vector, the velocity vector, except we're going to make it a little bit easier on ourselves and divide by the magnitude to get the unit vector. Basically, a vector tangent to the curve at time t that has a length of 1. So let me show you what I mean. Here in example 7, a particle moves in an elliptical path so that its position at any time t is greater than or equal to 0 is given by 4 sine of t, 2 cosine of t. So we want to find the velocity and acceleration vectors. Those are pretty straightforward. Those are just the derivatives as previously mentioned. Now we want to find the velocity, acceleration, speed, and direction of motion at t equals pi over 4. Well, the velocity at pi over 4 means I'm just going to plug in pi over 4 for t, and I get 2 square root 2 comma negative square root 2. Now remember, that also gives me a little bit of the direction too. I'm going to use that for my direction of motion in a few seconds. Acceleration, plug in pi over 4, and I get negative 2 square root 2 comma negative square root 2. Again, these are horizontal velocity and acceleration, and then vertical velocity and acceleration. Next, the speed. Speed is the absolute value of velocity or magnitude of velocity. Remember the airplane problem? We had a vector here and we used its magnitude to describe its speed, and this vector was the direction the plane was traveling, the velocity of this vector. The magnitude was then its speed. So we'll just calculate the magnitude of the velocity vector at pi over 4. So I found that and I got square root 10. Now, as far as the direction, we're using a unit vector. Yeah, so why aren't we using theta like we did here back with the airplane? Well, the airplane was traveling in the exact same direction every single time, so I could use an angle to represent it. I technically could do that same thing with this situation, but because we're moving not in the same direction every time, we're instead going to use a vector. So we're going to take the velocity vector at pi over 4, divide by the magnitude to make a unit vector. So this vector, 2 over square root 5 comma negative 1 over square root 5, has a magnitude of 1, a length of 1. Now, what does that mean pictorially? Well, here's your elliptical path that the particle is traveling on. We're not sure yet which way it's traveling, but just go with me here. So 2 over square root 5 comma negative 1 over square root 5, like I said, is going to be this tangent vector at time t equals pi over 4. So at t equals pi over 4, if I go back to where the particle is, the position, let's see, 4 times square root 2 over 2, and then 2 square root 2 over 2. Let's just call it right there. And then at t equals pi over 4, here's your teeny tiny little magnitude of 1 vector that's showing the actual direction the particle is traveling at that instant. 2 over square root 5 to the right, and 1 over square root 5 down. So it's going a little bit right and down. Now part C says sketch the path of the particle and show the velocity vector at the point 4 comma 0. Well, at the point 4 comma 0, I know that the position was 4 sine of t, 2 cosine of t, and that resulted in the point 4 comma 0, which that means if 4 times the sine of t equals 4, sine of t equals 1, and if 2 times the cosine of t equals 0, cosine of t equals 0, which will help me because in my velocity vector, I don't really know what time I got the point 4 comma 0 at. I mean, I could figure that out too, but instead, I'm just going to do a little simpler version. I'm going to plug in 0 for the cosine of t, and 1 for the sine of t. And that gets me the final velocity vector of 0, negative 2. That vector is at the point 4, 0, so whatever time that was, and it's going 0, negative 2, so it is vertically straight down. It has a magnitude of 2, so it's not technically our direction vector yet, but if I divide both coordinates by the magnitude, by 2, I get 0, negative 1, a teeny tiny little vector that shows the direction vector 2, just like we did here in part B. Now, does the particle travel clockwise or counterclockwise around the origin? Well, that's as intuitive as it seems, finally, right? The particle travels clockwise around the origin as indicated by the velocity vector at 4, 0. So, and really at the direction vector at t equals pi over 4, same thing. You can see those direction vectors show that this particle is traveling in a clockwise path. The now try problem number 35 says a particle moves in the plane so that its position at any time t is greater than or equal to 0 is given by x equals sine of 4t cosine t, product rule, and y equals sine of 2t. So part A, find the velocity and speed of the particle when t equals 5 pi over 4. Okay, so the velocity then, the velocity vector, again, got to use product rule, so don't forget about that for sine of 4t cosine t. And then sine of 4t, you're also using chain rule. What a mess. Then the y expression, the derivative of that, would be 2 cosine of 2t. Plug in pi over 4, and we get a big, long mess that simplifies very nicely down to 2 square root 2, 0. Who knew that 2 square root 2 was going to be simple one day? And then the speed of this particle is going to be the magnitude of that vector. So I calculate the magnitude, and I get 2 square root 2. Now part B says draw the path of the particle and show the velocity vector at t equals 5 pi over 4. Well, the path I found by putting the position for the horizontal, or the parameter for the horizontal position in x1, and the expression for the vertical position in y1, that parameter. Found a good window, and I get this, like, I don't know, mirrored hot air balloon looking thing. So we drew the path of the particle. Now we need to show the velocity vector at t equals 5 pi over 4. Well, I first have to figure out where 5 pi over 4 is in order to draw this vector. So I'm going to plug in 5 pi over 4 for my horizontal position parameter, and I get 0. For the vertical position, I get 1. So we're really dealing with the point 0, 1. Next, let's find the velocity vector at that time. So I'm going to plug in 5 pi over 4 to the velocity vector, and I get, what do you know, 2 square root 2, 0. I just did that on my own, which is 2.828, 0 to be able to draw this a little bit better. So this vector is going to be, it's going to start at 0, 1. It's going to go right 2.828 and up or down 0, so it's completely horizontal. So here's what this looks like, and I drew it to scale. Here's the point 0, 1, and then it's my x max only goes out to 2, and this is supposed to go out to 2.828, that vector is. So I drew it a little bit longer to kind of make it correct and accurate. Is the particle moving to the left or to the right when t equals 5 pi over 4? Again, my intuitive answer just says the particle is moving to the right when t equals 5 pi over 4, as evident by this time the velocity vector, not a direction vector, the velocity vector, which is direction, it's just not magnitude 1, so we don't call it our direction vector.